Last week we left off, we were kind of looking at what radiography is, what kind of inspections we do, and some of the key features with it. Biggest things are that it allows us to see both surface and subsurface flaws. That's a big advantage to it. Big disadvantage is we're dealing with hazardous radiation, and so there's a lot of safety precautions that we have to take, and on training and tracking and stuff like that that has to take place in order to do it safely and legally. There's the Nuclear Regulatory Commission is going to, you have to file permitting, and they do inspections and all that kind of thing that go along with any kind of radiographic sources. So today we're going to start off with radiation sources. And so when we're talking about radiography, there's two types that we're going to see out there. There are what are known as radioisotopes, and these are materials that emit radiation in the gamma range. And so, for instance, one of those that we use commonly is iridium 192. I've got a list on the next page that shows a bunch more, but that's probably the most common one you'll see. And so that is a radioactive isotope of iridium. The other thing we'll use, and probably more common, although not always, the advantage, we'll talk about advantages and disadvantages, but the other thing we'll use are X-rays, and that's man-made radiation. It's generated at the time of use. The nice part there is it can be turned on and off, right? When an X-ray tube is an electronic device, you turn power onto it to emit and generate X-rays. When you're done using it, you shut off power, and it stops emitting X-rays. And so, when it's off, when it's not powered, it's safe. But you don't want to be in front of it when power is applied. Radioisotopes, on the other hand, since they're a radioactive material, they're always going to be giving off that gamma radiation. And so they have to be kept inside of special enclosures, typically things that are lead lined or have other highly absorbing materials so that radiation doesn't get out into the environment. But if you are around it and don't realize it, you oftentimes won't know it until it's too late. So if any of you are interested in that, read some of the documentaries on Chernobyl and the firefighters who were putting out fires right next to pieces of the core that came out of the reactor to hear very graphic descriptions of what will happen if you're around radiation sources too much. But real quick, I'm just going to show a video. This is from the Canadian version of the Nuclear Regulatory Commission, and I think it gives a little bit more clear idea of what you're dealing with if you have, in both cases, radiation. So that gives you a kind of high-level idea of radiation if you either hadn't had it or it's been a while since you've talked about it. And some of the properties of it, half-life being one that's important. In the video, it talked about medicine. For us, it's also important if we're using radioactive elements in the imaging process, the radiography process. The one thing I did want to say here before we moved on, when I said radioisotopes, using that, why we use those over X-ray is that typically these radioisotopes, they're fairly small pieces of material. And so they can actually be put inside of things fairly easily, whereas an X-ray generation tube or an X-ray generator can't fit inside of many spaces. And so if we want to image, like I've got some pictures later where they want to look at kind of the parts of an engine without taking it apart, is they can actually take a piece of this iridium 192 and essentially slide it down the spool shaft in the center of the engine, and then put radiography film around the outside, and that'll provide an image where the radiation is traveling from the center of the engine out to be able to take images of things like combustion chambers and cases and stuff like that. So even though X-ray generally is safer nowadays and can be controlled more easily, there are applications where using a radioisotope is a more appropriate method, where you can do certain types of imaging that you wouldn't be able to do with an X-ray generator. So radioisotopes come in two forms. They can be either naturally occurring or man-made. And so things like, you've probably heard of radiocarbon dating. Carbon-14 is a naturally occurring radioisotope with a very, very long half-life. And so that's what's used when carbon dating, different objects or fossils or that kind of thing. Artificially produced are items that typically are produced in either a nuclear reactor or a positron of some kind, or a cyclotron. And so the case of you can have neutron rich that are produced in nuclear reactors where additional neutrons are added to that nucleus, which causes it to be unstable. You can also have proton rich, and in that case you use a cyclotron, a particle accelerator, to essentially knock neutrons off, leaving behind extra protons. And so both of those can be done. And so the atoms, once that's been done, they're going to decay, alpha and beta particles, and you will get the gamma ray energy coming off of that. And so what it means is, as these are giving off this gamma ray energy, it is a certain amount of energy that's passing through objects and tissues and other things that are nearby. That exposure is going to be based on time and half-life. Half-life being how strong of a how much radiation is the object giving off in a given period of time. And so we can adjust either one of those things when we're looking at the exposure. Is either we can add additional material, or we can use a material that gives off a larger amount of gamma rays at a given time, or we can increase or decrease the time that something is exposed to that material. And so it's a factor, those two items, the time of exposure as well as the strength of the gamma rays, or X-ray as well. It works the same way with X-rays. A few other common materials, radioisotopes, you'll see. So we talked about iridium-192. You can see that has a half-life of 74 days. You've got several other elements there ranging from, half-lives measured in days, ytterbium of 32 days for gamma radiography, up to some things have half-lives of in the years, right? Cesium-137, 33 years. It's a low intensity, so with the longer half-life, it's a lower intensity in that case. But just be aware that just because it's a lower intensity, you can see like cobalt-60 has a much higher, it's 5.3 years, but it's got a very high penetrating power. It's a very, very small gamma ray. And so it can also be used for sterilization, which means that it kills things very easily. And so you have to be careful with it when it's around, tissues and that kind of thing. It's one that you have to be extra careful when you're handling. And so, with any of these though, the half-life's important in two ways. One is the half-life, the strength, right, is potential exposure to the operator. The other part of it is, when you're figuring out the intensity, or how much you're going to expose an object as part of the imaging process, you have to know oftentimes where that element is in its half-lives, because the strength of the radiation field that it gives off is going to decrease, in half for iridium, for instance, every 74 days. And so a new piece, a piece that's just been enriched, is going to give off a lot more radiation than a piece that's 74 days old, or a piece that's 148 days old. And so you have to track that in order to be able to calculate your exposures. The other part of it is when the half-life, after so many half-lives, and depending on the material and the time and the strength of field, it won't be giving off enough radiation for it to be useful anymore. And so again, they have essentially a shelf life. There's a point where they've expired, and you would need to get a new batch of an element in order to use it, for it to work effectively. So I mentioned earlier radiation for exposure. How much radiation do you get? It's a function of time and intensity. And this applies to both your imaging process, what you need to get the image that you're looking for. as well as to the hazard that it can pose to you as the user of it. And so to mitigate that hazard, we're going to have different ways of monitoring that exposure. So one is area monitors. If you have like a lab setting where you're doing a lot of radiography in a given area, you might have permanent systems to monitor this kind of thing. Other things are known as interlocks. You know, an example of an interlock is like your microwave, right? A microwave is a radiation source. But as soon as you open the door, if your microwave's running, if you pull that door open or you pop the little latch on it, it immediately shuts the microwave off so that you don't get, microwaved by opening the door while it's running. So that's an interlock mechanism where essentially the radiation source, whether it's a shutter that closes the enclosure for a gamma ray source, or something that cuts the power to the X-ray generating device, as soon as you open a door, open an enclosure, something like that, it automatically isolates you and the object from whatever the radiation source is. Personnel exit monitors, if you're going in and out of an area, that's essentially a Geiger type counter that is at like a doorway or in an airlock area that's going to look at how much radiation you are now giving off as you leave an area in case you get dust on you or other stuff like that. And then portable instruments, survey meters, Geiger counters. I'm sure everyone's seen those in movies and stuff like that. The little boxes they walk around with that make the clicking noises, right? They got a little thing on them. Again, go watch the Chernobyl series. You'll see that if you're interested. But what we're looking at, the unit of measurement is called the REM, and it's the radiation dosage to a human. It's approximately equal to 1 Roentgen, which is the amount of 1 electrostatic unit of positive or negative ionic charge in 1 cubic centimeter of air under standard conditions. Basically, it's how many radioactive particles are in a cubic centimeter of air. And so the higher that is, the stronger it is, the more radiation there is in the air, the more radioactive particles there are. So half-lives are based on, it's a statistical measurement. So we use it to measure the strength of the field, but know that at the end of the day, it is based purely on statistics. And that is the length of time where there's a 50% chance that an atom will have undergone nuclear decay. So not every atom in your material is going to decay at exactly the same rate. So some of them are going to peter out or snuff out faster than others. So that half-life is based on when will half of those have no longer be producing or giving off any kind of radiation. Okay, now the whole chunk of material as a whole, right, has billions of atoms in it, and so it's the nucleus giving off losing those neutrons or protons. They aren't all going to do it at the same rate. This nucleus might give off 1, this one may not have given off. It depends on collisions inside the atom and that kind of thing. And so half-life is based on what we see it as if we measure the amount of radiation being given off. At the half-life point, that amount of radiation overall is going to be half of what it was when that element first came into existence. And again, oftentimes that is for what we're using for industrial purposes, they are man-made radioactive elements versus natural. Natural radioactive elements, the ones that are naturally occurring radioactive elements for the most part have very, very long half-lives. Any of those that were natural when elements first formed, if they had a short half-life, they've burned out long ago. And so something like carbon-14 that has half-lives in, I don't remember how long it is, it's long enough to measure million-year time periods, that we see those, but they don't give off, right? There's carbon-14 in all of us. We don't feel, there's not a lot of radiation present from it because it is such a long half-life, it gives off such a little bit at a given time. So for us, after a half-life, the amount of radiation given off by your chunk of material has cut in half. And again, it cuts in half at another half-life, taking it to a quarter. And after another half-life, it drops down to an eighth, and then a 16th, and a 32nd, and a 64th, and a 128th, and a 250th. So there's a point where it's effectively zero. It never officially goes to zero, right? You can keep dividing that into a smaller and smaller fraction. But there's a point where it's essentially no longer giving off radiation because it's such a small amount of the original that it would have. So with these, we have to be able to control them. So this is kind of a diagram of if we're dealing with gamma radiography using materials. This is a simplified diagram of a isotope delivery system. And so what you have is that some kind of a shielded storage device. You have what's called a drive cable, and you have your source as a little piece of material on the end. And then it has a tube coming off of it that we can insert into whatever it is that we're going to be imaging. And so these allow us, this crank out device and drive cable allows us to stand away from that box, that source and shielding, and ultimately the delivery tube over here on the right, so that we can be a safe distance away, or we can put some kind of a shield between us, like a lead blanket or a lead curtain, and then be able to you move this crank to move that source, that gamma ray source, out into whatever it is we're going to be imaging. So you move it along, and when it gets to the end, there's something called a collimator, which is basically, it has another kind of little chamber where it's only going to allow that radiation to escape in a given direction. Okay, and so now it would be at its position, and if we put an object here below this source, or below this collimator, and then put some film down here at the bottom, we would be able to create a radiographic image using this gamma ray source from a distance. Looking at the tip of one of these, there's something like this. And so you have, here's the radioisotope material. You can see is the small ball. It goes inside of this little delivery chamber. Here's the end of that cable. And that would be put into your object. And so I do have a video there on your own if you want to watch that. It just shows one of these things in action. But here's kind of the setup of it. This is out of a manual, and this is what I was talking about earlier, where if we want to image, in this case, they're imaging the combustion chamber. So you have either a can or an annular type combustion chamber. Here's the inlet side of the engine over here on the left. You know, and you've all looked in like our JT9, right? You pull that spinner cap off and you can see there's that spool shaft that goes all the way down to the back end of the engine, right? It's a big tube through the engine. Well, you run your source through the spinner, down through the center of the engine, a certain distance back, it's going to be here's your turbines back here on the right. It's going to be, in the area of the combustion chamber. And then they've placed a piece of film, just outside the combustion chamber in like the bypass or something like that. And it looks like this when you have it set up outside. Okay, so they've got I believe this is a JT9. They've got the camera going in. I know it's not a great picture. It's hard to find good pictures of this stuff. It's not like people do this every day. And, there's going to be a piece of film over here somewhere. Again, you can't really see it great, and what you get is an image that looks something like this. So here's a liner can that has been imaged while on wing. Here it's on a stand, but you could potentially do this hanging from the pylon of the engine, not actually have to remove it in order to do the job. Pop the spinner off, run your source down the center, put your film on the outside, pop open the cowls, put your film on the outside, and you're able to do a image. And hopefully you've had enough experience with turbine engines now. I know I had you all for turbines class, where you could identify some things on here. What do you see? What are you able to see on here? I'm talking just features, non-relevant indications here. I'm not asking for you to diagnose if this is airworthy or not. What's that? You got all the tabs for the cooling air. You can see the lines that divide the tabs, right? What else? What are all these black circles? What's that? There are holes in it, right? They have different holes for air to pass through, right? So you can already identify some of the items here. If you look at it closely, if you were better trained in this, you might be able to see damage or something like that. You could see potentially a crack emanating off of one of these, cooling tab slots or something along those lines. The other way we can do this is to use an X-ray tube. And an X-ray tube is essentially it's a cathode ray tube. It uses a high voltage source, so high voltage power supply. Okay, you have a low voltage source over here that is going to generate an electron beam, and then that high voltage source creates a big potential between the electron generator over here and a anode target structure over here on the right. And so as those electrons, you basically generate free electrons. They get pulled left to right, and when they strike a target material, that creates high energy collisions in that target material and forms an X-ray beam that comes off 90 degrees to that. And then we could put our object in line with this X-ray beam with a piece of film or a detection plate behind it and be able to image it. I assume, has everybody had X-rays at least at the dentist at some point? Right? Okay, so the thing they shove in your mouth, about yay big, whether it's a little piece of film or it's got a wire coming out of it, that's the detector. That goes on the inside of your teeth. And then they bring that thing down here and they put it right by your cheek, right? That's your X-ray source. So the X-rays are passing from that thing that hangs from the ceiling through your teeth and into that film or detector that's on the inside of your mouth. Okay? That's a very low dosage X-ray. Okay. And so if we see one of these in operation, it's going to look something like this. Let me pause this. Okay. So we've got two different ways to have our radiographic source, right? Our gamma material and then our X-ray. Those, whether it's the photon radiation of X-ray or the gamma rays that come off of a gamma radiography source, is going to pass through our object, and then we're going to use some kind of a detection method to see them on the other side. And so the oldest method for doing this was using film that had a silver salt. And silver salt is silver with a salt ion. So you're used to like sodium chloride as table salt. You can make salts that have silver in there, like a silver chloride or something along those lines. And they tend to be, those materials react to, in this case, the different radiation sources. Maybe not, I'm about to date. Camera film, if you've worked with camera film, that's a film that's reactive to visible light, to wavelengths of energy in the visible spectrum. This is another form of film that is reactive to wavelengths in the X-ray or gamma ray spectrum. Okay? These were either single or two-dimensional. What you've probably seen most often would be a two-dimensional image. If you've, again, going back to the dentist example, the images you've seen of either your teeth, or if you've ever had X-rays done at a hospital or doctor's office for something like a bone or a joint or something like that. Those are two-dimensional X-ray where it gives you a picture of what you're looking at. Disadvantages to that is that, that just like any other film, it has to be processed. And so the image is taken, and then that film has to go through processing and, with different chemicals and things like that. And then ultimately a print is made, or a negative essentially is made that you can view. And so that takes time, considerable expense, and there's obviously a lot of skill. There's skill involved in that processing. Modern day is we've gone to real-time detection. So detectors that are, semiconductors that can sense those different radiation sources striking the semiconductor. And so you can take that, you take those detectors, they sense the fact that there is radiation striking that semiconductor. They can sense the intensity of the radiation striking that semiconductor. And you have a lot of those laid out in a grid to create essentially pixels. And you can use that to construct a 2D image with a computer. You feed that data, essentially the field strength, the radiation field strength at all these different points. You feed that into a computer and it can create an image using that. And it does that in real time. Sometimes it's still frames, individual captures. Sometimes it's video, multiple. It can take just continuous captures over time to create a video presentation of it. Those are almost always two-dimensional. Okay? Again, most common. But now you have the ability to start taking a three-dimensional image. And that's what is commonly known as computed tomography, or CT. So if you've ever had a CT scan, that's the medical application of this technology. But we can take that same type of imaging and apply it to objects in aviation or other industrial processes. And so that allows us to reconstruct an image, and then we can have slices or a full 3D image. We can actually kind of fly through a part, so to speak, and be able to see how something is. So you're very familiar with two-dimensional. You're probably somewhat familiar with three-dimensional. You've all seen these things either on TV or in person. One-dimensional looks like this, and so that is just over distance, how much radiation is able to pass through. You can see it kind of looks like an A scan. If you have like a combustion chamber, if you were to lay that same combustion chamber here, it would say, okay, at different distances, you have different intensities of radiation coming through. Here's a normal profile, and you compare that to a non-normal profile. But again, not super useful, don't see it too much anymore. Here's two-dimensional film, X-ray of a composite material. And so this is you've seen these buildups where you have an area where you have a few layers of composite that are, it's just the fiberglass, and then it kind of slopes up and into an area that's cored with a honeycomb core. That's what you're seeing here. So here's the edge that's not cored, and then you can see it kind of gets thicker, and this is the area where it's fully cored. In this case, remember, white is where the radiation doesn't pass as easily. And so what you're seeing here is there's thinner layers of epoxy kind of in this area. The radiation actually passes through, the honeycomb and the fiberglass and the resin in different amounts. And so you can see those differences. And you can see things like, how much. You can see like an area with less epoxy here than there is over here, okay? You have more radiation able to get through these cells that have less epoxy filling them than the full cells that are further to the middle. You've probably also seen two-dimensional X-ray used at the airport, right? This would be a bag going through the X-ray scanner, right, for carry-on baggage and that kind of thing. I don't know how many belts one person needs, but they got at least 3 belt buckles sitting here. We kind of went through it one time and figured out what some of the stuff was. I want to say that was a laptop, hair dryer, right? Not sure what this is down here. Some tent poles, maybe. But, tripod. There you go. It's a tripod. That sounds about right. Anyways, gotta be. So, you can kind of figure out, obviously with training and a trained eye, you start to, newer ones nowadays, computer algorithms end up picking out most of the stuff that's in there. They're going to look for certain intensities, materials that are known to be suspect that allow a certain amount of radiation to pass through, plastic explosives and that kind of thing. they can be tuned to automatically detect those kinds of situations. Computed tomography, when we want to get a 3D version of this, we have to now sweep or move things around in order to do that. Typically, if you have all stationary objects, the best it's going to do is a 2D dimension. So here's a pretty common setup: is you have an X-ray tube that can kind of sweep side to side. It creates a fan beam with a detector that can detect over a distance, and then the test piece can be moved up and down in that beam, and that would create essentially cross-sectional slices that can then all be stacked on top of one another to create a 3D image. Or a 3D representation. Another version of this, here's another sweeping type, X-ray source, sweeping left and right. You have a linear detector, and now not only can you move the detector and the X-ray source up and down, but the part itself can be rotated to look at it from different angles. And so this is the type of equipment you would see where you can produce, and then, again, a part where you can essentially section it from any angle. You can do kind of a fly through of it. And these are used oftentimes for things like fan blades or turbine blades to look at internal passageways. So remember, a lot of turbine blades have cooling passages inside of them. And when they're being manufactured, you want to make sure that those passages are clear. When they're being overhauled, you want to make sure they're clear. And so this is a CT scan. Now, this is just one slice of it. They would take many, many slices of this, many images at different locations. But if you lay them all on top of each other, you can get an image that looks like this. And so now you can really start to look in there to look for damage or for clogged cooling passages, or cracks or flaws of that nature. And so you're seeing this more. So again, this would be something used in a back shop typically, an engine overhaul shop where they're going to overhaul the blades. They want to know exactly which turbine blades can be reused, which ones have to be changed out, or things like that. Or it could be a dedicated NDT shop where something like an engine overhaul shop or an airline, they would send their blades in to a shop that has one of these X-rays, and they're able to do it. Just from a economic side of it, a basic X-ray system, basic 2D X-ray system to do something like a blade, you're talking probably about in the $120,000 range to get your X-ray source and detector and computers to drive it. To get into a 3D C-scan type, CT scan type thing, you're talking probably at $500,000 to $1 million. And so again, this isn't going to be just Joe's overhaul shop. It's going to be some kind of a dedicated facility, or it's going to be a manufacturer that's going to use this. But again, you would be sending stuff to the CT scanner to be looked at if it needs that level of investigation. Okay. So that ends radiography. So